last BRE, so we're talking about BRE, okay? The last BRE is Poisson distribution. And you do this when you have some assumption. So if on average lambda number of event occurs in a unit of time, and here we are going to assume that the unit of time could be anything. It could be like hour or a day or something. Okay. And then plus some additional conditions, which I'll elaborate later. Additional conditions. You can say that the probability of having, I should define the random variable first. So x is the number of the same kind of events occurred in 1 unit of time. See, in a probability distribution, when you say, this event only happens once in, like this hurricane, this category 5 hurricane only happens once in every 20 years, okay? So if that's like the average that you're given, it doesn't mean that within a given 20-year period, you get exactly 1 hurricane. You might get 2 hurricanes, you might get 0 or something like that, right? Okay? So let's say another example will be there is this bridge where the number of cars that pass through every hour is something like 150 on average. Does that mean at every hour it's exactly 150? No, sometimes it will be above 150, sometimes it will be below 150, right? And you may have to model that situation, okay? So if such, yes?
Sorry, I just can't see.
Sorry. Let me just read again. Sorry.
Next to unit of time, yeah.
Yeah, unit of time. Okay, so if on average lambda number of event occurs in a unit of time, plus some additional conditions, which I don't want to say now, okay? A little bit more conditions, okay? Then we have this Poisson distribution, which says the probability of x equals to exactly k is equal to lambda to the kth power e to the negative lambda times lambda, no, k factorial. I think that's right. Right? Yeah, that's right. Okay. Now let me talk about some additional assumptions here. So the additional assumption is that additional assumptions. Okay. So there's a finer interval of time that the event occurs with a fixed probability. So, you know, a lot of times this won't be a good model because if your unit of time is a day and you're talking about number of customers per day, some hours you might have more people and some hours you might have less, right? So you want this to be somewhat evenly distributed. So that a lot of times this one immediately makes this BRE unusable, but you know, it could still be pretty close to the real model, even if this is not met. Another thing is, in that time interval, in that finer time interval, the event cannot happen more than once. And that's a reasonable assumption because if the event, if the finer time interval is very small, then the probability of two things happening twice will be, if the event is p, then happening twice would be p squared, p times p, right? And p is like 0.001, then p squared is even smaller. So that's not a unreasonable condition to ask. Often this is easy. And the third condition is that probability is independent of previous time intervals, occurrences. So if something happens, let's say, oh, we had a good day, like yesterday we had 1,000 customers. And does that mean today we're going to have a lot more customers than usual? We don't know. It's kind of, if it doesn't tell you anything about what's going to happen later, then this is the probability distribution that we use. Somewhat related to this would be the exponential distribution, which is not in here because we're only doing discrete probability, and there's a continuous probability that's very closely tied to this one. And the exponential probability, I don't have time to do it today, but I'll explain in the next class. And it will be, it will have something called a memoryless property. See, knowing that something happened doesn't change whether it's going to happen again or not in the future. You just don't have any other idea than this average. All right. So here's an example. Suppose on average 3 cars pass over a bridge per hour. Okay? And let's say if the number of cars passing in an hour follows Poisson distribution. What is the probability that P of x equals to 5? So maybe you're trying to build a bridge in a remote place. You want to know how much stress the bridge is going to get by the number of cars passing, all that, and you want to have a good model for it. Then, using the Poisson distribution, you're going to say, well, this is the case where lambda is what? 3, right? So probability that x is equal to 5, where lambda is 3, so k is 5. So I just use this formula with k being 5. E to the negative 5 over 5 factorial. 5 factorial is 120, right? So can somebody do this quickly? Yeah.
Isn't it e to the negative 3?
Oh, thank you. No, e to the negative 3. Yeah, e to the negative 3. Thank you. Yeah. E to the negative 3. So what do you get? This is 243 times e to the negative 3 times divided by 120. Yeah. So yeah, that's more likely. So there's only 10% chance that you would have 5. Okay. And I guess realistically what you really want to do is the probability of having something or more. So it's like, what's the probability of getting 10 or more cars on this bridge where the average is 3? Okay. So it'd be like P of x equals to 10 plus P of x equals to 11, P of x equals to 12, and so on and so on.